On July 1, 2025, astronomers observed a remarkable object hurtling through our solar system at an unprecedented velocity, nearly twice that of the previous interstellar visitors, Oumuamua and comet Borisov. This new visitor, later confirmed to be an interstellar comet, immediately drew attention not only because of its speed, but also due to the unusual properties of its nucleus and the implications it had for our understanding of interstellar objects. Early observations suggested that the comet was enveloped in its own dusty coma, a hallmark of cometary activity, and preliminary measurements indicated it was significantly larger than both Oumuamua and Borisov. Initial estimates suggested the comet's nucleus, the solid rocky core distinct from its gaseous and dusty outer layers, spanned approximately 5.6 kilometers, around 3.5 miles in diameter, a size that was unusually large for an object entering our solar system from interstellar space. Measuring the size of a comet is notoriously challenging. Unlike asteroids, which are typically solid and relatively straightforward to measure, comets have comas, clouds of gas and dust that are expelled as they heat up while approaching the sun. This outgassing process occurs in stages. First, the comet begins to release gas as solar radiation warms its surface, and later, as the comet draws even closer to the sun, dust particles are also ejected. These emissions create the iconic glowing halo and tail associated with comets. However, outgassing acts like a natural thruster, subtly altering the comet's trajectory, rotation, and velocity. This makes direct measurements of the nucleus difficult, because astronomers must account for the influence of these outgassing effects in order to estimate the actual size and mass of the comet's solid core. In a new study, which has not yet undergone peer review, a team of researchers from Harvard University, including Richard Cloete, Avi Loeb, and Peter Verez, examined a large dataset compiled by the Minor Planet Center, spanning observations from May 15 to September 23, 2025, sourced from 227 observatories worldwide. Their aim was to determine how much of the comet's movement could be explained purely by gravitational forces, as opposed to non-gravitational influences such as outgassing. The researchers found that the non-gravitational acceleration of the object was remarkably small, less than 15 meters per day squared, which is minimal given the observed outgassing activity. Observations from the James Webb Space Telescope had previously indicated that the comet was shedding mass at an astonishing rate of roughly 150 kilograms, around 330 pounds, per second. Despite this, the comet's acceleration remained largely unaffected, suggesting a substantial and resilient nucleus. Based on these calculations, the team estimated the comet's mass to exceed 33 billion tons, or 33 trillion kilograms, and reinforced the nucleus size estimate at approximately 5 kilometers, 3.1 miles, across. Although this is a considerable mass for a comet, it is dwarfed by the record-holding C/2014 UN-271, also known as Bernardinelli-Bernstein, which weighs an estimated 500 trillion tons, or 5 times 10 to the power of 17 kilograms, and possesses a nucleus measuring 128 kilometers, roughly 80 miles, in diameter, the largest ever observed. However, what sets this new interstellar visitor apart is not just its size, but the rarity of such massive objects entering the solar system from interstellar space. Avi Loeb has highlighted the anomaly posed by this discovery, emphasizing that the object is far more massive than the previously observed interstellar objects, 1I/Oumuamua and 2I/Borisov, by a factor of 3 to 5 orders of magnitude. Given the expected distribution of interstellar material and the estimated number of smaller interstellar objects, astronomers anticipated discovering thousands of smaller objects before encountering one of this scale, making 3I/Atlas a notable outlier in interstellar studies. The apparent scarcity of interstellar objects of varying sizes has long puzzled scientists. Loeb points out that if interstellar space contained a substantial population of smaller rocky bodies, similar to the scale of Oumuamua, we should have detected tens of thousands of such objects by now. Yet, prior to the discovery of 3I/Atlas, only 2 interstellar visitors had been observed. This discrepancy suggests either a gap in our detection capabilities or a unique origin for 3I/Atlas that sets it apart from typical interstellar debris. If future observations confirm the size and mass estimates, the object would represent a substantial anomaly in the population of interstellar comets, challenging existing models of the formation and distribution of rocky material between star systems. Loeb, known for his provocative interpretations of astronomical data, has once again raised the possibility, albeit a highly speculative one, that 3I/Atlas might not be a natural object at all. In his discussion of the comet's properties, Loeb notes that the mass of 3I/Atlas scales with the cube of its diameter. Should the nucleus be found to be even larger than the currently estimated 5 kilometers, the likelihood that it originates solely from a natural interstellar mass reservoir becomes increasingly untenable. Loeb points out additional unusual characteristics, such as the object's trajectory, which aligns closely with the ecliptic plane, a statistically improbable occurrence with a chance of roughly 1 in 500. Furthermore, he cites the detection of nickel without accompanying iron, a combination reminiscent of industrially manufactured alloys. Taken together, Loeb argues, these factors could, in theory, point to a technological origin, suggesting the object might be an artifact rather than a conventional comet. Despite these intriguing claims, the broader astronomical community remains cautious. NASA and other planetary scientists have emphasized that the behavior of 3I/Atlas strongly resembles that of a natural comet. Tom Statler, NASA's lead scientist for small solar system bodies, acknowledged the comet's peculiarities, but underscored that its overall behavior, such as outgassing trajectory and reaction to solar heating, is consistent with known cometary physics. According to Statler, while the comet displays some unusual properties compared to typical comets in our solar system, the overwhelming evidence supports the conclusion that it is a natural object. This perspective highlights the need for rigorous data analysis and careful interpretation when examining extraordinary claims, particularly those suggesting non-natural origins for celestial objects. The discovery of 3I/Atlas is significant not only because of its size and velocity, but also because it offers a rare opportunity to study an interstellar visitor in detail. Unlike previous interstellar objects, which were smaller and passed relatively quickly through the inner solar system, this comet presents a chance to examine the dynamics of outgassing, the physical properties of its nucleus, and its overall composition with modern instruments, such as the James Webb Space Telescope and various ground-based observatories. Understanding the behavior of such an object can provide valuable insights into the types of materials that exist beyond our solar system and the processes that shape interstellar debris. Moreover, the mass and size of 3I/Atlas raise questions about the formation and evolution of interstellar comets. How could such a massive object remain undetected for so long, given the extensive surveys of the sky conducted by astronomers over the past decades? Could there be entire populations of similar objects drifting through interstellar space, invisible to our current instruments, waiting to be discovered? These questions drive ongoing observational campaigns and theoretical studies, as scientists attempt to reconcile the discovery with existing models of stellar and planetary formation, as well as the dynamics of small bodies in interstellar space. While speculative ideas about alien origins capture the public imagination, the scientific method requires careful measurement, repeated observation, and cautious interpretation. The excitement surrounding 3I/Atlas underscores the broader allure of astronomy. Each new object provides a window into the unknown and challenges researchers to refine their understanding of the cosmos. Whether it is confirmed as an extraordinarily large natural comet or, in the unlikely scenario suggested by Loeb, a technological artifact, 3I/Atlas has already reshaped the conversation about interstellar objects and highlighted the remarkable diversity of bodies traveling through our galaxy. In conclusion, the observation of 3I/Atlas represents a milestone in interstellar astronomy, combining record-breaking velocity, unusual mass, and an intriguing trajectory with a highly active coma. The ongoing study of this comet promises to enhance our understanding of both cometary physics and the distribution of interstellar material, while also sparking discussion about the limits of natural explanations and the tantalizing, though improbable, possibility of technological origins. As astronomers continue to gather and analyze data, 3I/Atlas stands as a reminder of the surprises that await in the vast reaches of space, challenging our assumptions and inviting humanity to explore the mysteries of the cosmos with ever-increasing curiosity and sophistication.